So before we move to the code, let me introduce to the domain that the code is going to be working in. It's a social networking app that we use in a lot of our training engagements. It's called Shouty. And here is a 30-second elevator pitch or brief description of Shouty taken from Cucumber School, which is our online video training for Cucumber.
Shouty is a social network that allows people who are physically close to communicate, just like people have always communicated with their voices. In the real world, you can talk to someone in the same room or across the street, or even 100 meters away from you in a park. If you shout, that's shouty. What you say in this social network can only be heard by people who are nearby.
As you can see, I've got a small project open inside IntelliJ. What we're looking at the moment is the feature file. You can see on the left, it's called hereshout.feature. A feature file is just a plain text file with a .feature extension, and it needs to conform to the Gherkin syntax. So Gherkin's quite simple. It's documented online. You can find documentation on our blogs and in our books. But simply, it starts with a keyword, feature, followed by a colon, and then a title for your feature. In this case, the feature is that you can hear a shout. There's then a space where you can put freeform documentation, comments, or other text. What we recommend you use this space for is to list out the rules, the business rules, that are being illustrated by the examples in this feature file. So in another way of saying this is that you list out the acceptance criteria that would satisfy this feature. Then the next keyword you see is scenario. This introduces one of the concrete examples that you will have translated, what you will have captured at your Three Amigos workshop, and then you'll have written out and transcribed them in the given when then format. Again, following the colon is a name, a title. We use something called the friends naming scheme. So this is the one where an in-range shout is heard. This scenario title is then followed by some steps, which are introduced by keywords given, when, then. There's also a conjunction here, and, which helps make the scenario read nicely. So let's try reading out. Given Lucy is at 00 and Sean is at 0900, when Sean shouts, then Lucy should hear Sean. So this is, I'm hoping that this is quite straightforward and quite clear for you. What's happening is that we're setting up a context, which is the system, Shouty, now understands that Lucy is at one particular location, Sean is at another location. We've arranged it such that those two locations are less than 1,000 meters apart. And therefore, when one of the participants shouts, the other one should be able to hear that shout. We then have a second scenario in this feature file, the one where an out-of-range shout is not heard. We're setting up the context slightly differently. Lucy is still at 00, but this time Sean is at 1100. Therefore, Lucy and Sean are 1100 meters apart. So now when Sean shouts, Lucy should hear nothing. So already we have a human readable specification. And the goal is to make sure that this human readable specification actually does then lead to automation that drives the underlying system that can verify whether this system works or not. So let's try that out using IntelliJ. So over here in the Project Explorer, I'm going to right-click on the hereshout.feature feature file, which then throws up loads of options, as you might expect from modern IDEs. And the one I'm going to select is run the feature hereshout. Now, what this is going to do is it's going to instruct IntelliJ to invoke Cucumber. It's going to ask Cucumber to run all of the scenarios that are in the hereshout feature and report the results to us. So let's see what happens. It runs quite quickly. It starts off, it runs all of the steps found in the two scenarios, and we get a green bar because they all pass. we kind of hope that means that our application is conforming to these two examples. And let's dig into this a little bit more deeply. So, how does Cucumber know what automation code to run in response to each of the steps in the feature file? Let's take a look at this class, Shout Steps, which is in the test part of the Shouty project. It's a plain Java class. There's nothing fancy about the class itself, and it contains a number of public void methods, each of which is annotated using a Cucumber annotation. There are 3 Cucumber annotations available: given, when, and then. The annotation itself, whether you choose to use given, when, or then, is not important. Cucumber pays no attention whatsoever. It behaves exactly the same no matter which one of those you choose. The important thing is the text that follows between the double quotes. This is a regular expression. I won't be going into details about regular expressions. They are well documented all over the internet and in many computer science texts. So how does it all work? Well, Cucumber reads a step from the feature file. It takes the text that comes after the keyword, so anything that comes after given, and, when, or then, and then it tries to match that text against the regular expressions that have been registered in the step definition file using the Cucumber annotations. If it finds one and only one that matches, it then calls the corresponding method. So it's all down to regular expression text matching. There's a few things about this regular expression that may not be immediately obvious. So for instance, there's a little caret right at the beginning of the text string, and there's a dollar symbol at the end of the text string. Clearly, there's no caret or dollar sign in the feature file. These are, in fact, special characters in the regular expression library. The caret represents the start of a string, and the dollar represents the end of a string. So what this regular expression means is that it will match a string that says Sean shouts and nothing else. So if I was to edit the feature file and change the step to read Sean shouts obscenity, then we would see that it would not match. So let's do that, and we can run it again, and we'll see that step definition is going to come up as being in error because it hasn't matched. However, if I go through to the step definition itself and I take out this dollar sign, that means this regular expression is no longer going to match against the end of the string. So in fact, this should now work as before because the obscenity is going to get ignored, as it should always be ignored. So what we've got is a regular expression that's quite pedantic about how you express it. It's so pedantic that actually white space is often something that causes people a lot of problems. So let's go back and set it back to where we were at the beginning. And make sure that it's going to run green again. So it's still green, that's great. Now if I put an extra space between Sean and Sean shouts, and then try running that, you will see that it fails. And it fails because the regular expression library is very precise. So if you get errors like this, it's worth making sure that you are happy with that your white space in your feature file is the same as the white space that is in your regular expression. Okay, check we're green. Good. Let's go back to the step definition file. So this is a very simple step. It matches just the text and it calls the methods accordingly. There are some more complex steps above, which are the ones that set up where Lucy and Sean are located. And you'll see that they include some characters that are introduced with a parentheses. Now, parentheses, again, are special characters in regular expressions, and they introduce something called a capture group. This is because, in general, with a regular expression, you just want to know, did my text string match the regular expression or not? But sometimes you actually want to know what text matched. So the \d here matches against any digit. So in our particular case here, we're trying to set up a coordinate. So we want to know what the coordinates are for Lucy and Sean. And so we really want to capture them from the string we're matching against this regular expression so that we can then pass them as parameters into the step definition that's associated with it. So I guess the thing to bear in mind is that whenever you see a capture group in a Cucumber regular expression, that corresponds to a parameter in the step definition that is associated with that regular expression. So let's think about this. We're passing in 2 digits to the coordinate x and y. We're also matching the word Lucy, and we're also using the word Lucy in the method call to set location. So when we say Lucy is at a particular coordinate, we are in fact using the text string Lucy when we call our shouty object. So in fact, we could parameterize this. So let us put Lucy in parentheses, introducing a new capture group. It's the first capture group in the regular expression, and we now have 3 capture groups in the regular expression. Each one of those has got to have a corresponding parameter in our step definition. Currently, we've only got 2 parameters, so we have to introduce a third. Let us call it name. It's a string type, and we have to put it in first because Cucumber allocates the capture groups in order of finding them within the regular expression when it calls the step definition. However, now we're getting the name passed in. We will probably get this to pass perfectly happily. We haven't changed anything in the step definition implementation. But now we've got this parameter name, which means that, in fact, we can replace that string constant with the variable name. And because the value Lucy is the same as the string constant Lucy, everything still works fine. We've now got a step definition which is parameterized to take the string Lucy, but of course we could make this into a wildcard. So there is another wildcard which is \w, which stands for word character, and this will match any string of any sequence of word characters which are A to Z. And Lucy, of course, is one of those strings of word characters. So let's run it. Now, this time when it runs, we actually get an error. The error that we get is maybe not one that you're expecting. It's called ambiguous step definitions. The reason we've got an ambiguous step definition is that \w, this capture group \w plus, will match, as I said, any sequence of word characters. Lucy is one sequence of word characters, but Sean is another sequence of word characters. And the only difference between these 2 regular expressions now is that this one will only match Sean, but this one will match Lucy, Sean, and in fact, any sequence of word characters. And so when we get to a step that says Sean is at, Cucumber finds that there are 2 regular expressions that match. The first one, which has got the wildcard, and the second one, which is just for Sean. At that point, Cucumber doesn't know which one of those you want it to call. And rather than make a guess, it just signals an error. Now that we have parameterized this first regular expression, we can in fact delete this the second step definition, because the first one will now cover both Lucy and Sean, and in fact any other participants that we choose to add. At this point, we should have a look at the name of this step definition, because the name is no longer truthful. It's not just Lucy. So let's rename that to person is at. The name itself is irrelevant. Cucumber is not going to look at the name of the step definition method, but other people, other automation engineers, and indeed yourself will read this at a later date. So it's a very good idea to always make sure that you keep your names truthful and descriptive. And then we check to make sure that everything is still running green, and we can move on. So we've seen that if there is more than one regular expression that matches a step, Cucumber will signal an error using an ambiguous step definition. And we'll have to go and sort something out and make sure that we've got our regular expressions correct. Equally, if we have some text that doesn't match any regular expression, let's change that to Oscar, what we get is also an error because Cucumber tries to find a step definition to run and finds that it can't. The error that gets signaled is an undefined step error. If you're doing this from the command line using invoking Cucumber directly, what Cucumber does is it emits something called a snippet, so which is some sample text, sample step definition that will satisfy this regular expression. IntelliJ will also do that for us, and it does it quite happily through one of the automation points that within the IDE. So let's create this step definition, and we're going to create it in the shout steps step definition class that we already have. And so this is what has been generated for us. It's now a regular expression that says Oscar shouts, and the method is called Oscar shouts. This may be what you want, and then all you have to do is go into the body of the step definition and express the automation that you would like to take place in response to this step. At the moment, what we have, though, is we have a template. And the template throws an exception called a pending exception. A pending exception is a Cucumber provided exception, which signals to Cucumber that this is work in progress. The reason that we have a pending exception is because sometimes we want work in progress to fail the build, probably before we put it into production. But sometimes we would like work in progress to not fail the build, possibly at an earlier stage of your CI pipeline. So Cucumber, especially when you start putting it into your CI system and invoking it from there, and allows you to choose whether to run in strict mode or not strict mode. By default, it runs not in strict mode, which means that pending exceptions do not fail the build. What we haven't really said explicitly, but we should say now, is that any other exception that is thrown from a step definition causes the scenario to fail. It causes all subsequent steps within that scenario to be not run, and it causes the build overall to signal a failure. This is the only way that Cucumber recognizes that a step definition has failed or not. So a step definition that does not throw an exception has succeeded, has passed. A step definition that does throw an exception has failed. Let's demonstrate this. So let's delete these lines. So now we have a step definition called Oscar shouts, which does nothing at all. And what happens when you run the application? Oh, well, it all passes, even though nothing is going on here. So this is maybe a neat trick, which is that if you ever want a step definition to pass, well, you just delete all the code in it. This is not useful, but it lets you understand how errors are signaled between Cucumber and the step definitions get invoked. Now let's take this back out again. We don't want to have Oscar in here just yet. And we have to take him out of the feature file as well. And make sure that everything is still at green. Good. Now I'd like to introduce you into something called a scenario outline. So if we look at these two scenarios, they're quite similar. They both have Lucy and Sean being set up at locations. They both have Sean shouting, and the outcome is different. One of them hears Lucy hears Sean, and the other one, Lucy should hear nothing. So quite often we find that we have a number of examples that end up looking very similar. And if we had to write them all out in longhand over and over again, that would be tedious for us to write out. And it would be tedious for our users and our product owner to read that sort of documentation. So Cucumber provides us with something called a scenario outline. And I've prepared one earlier, and I'm just going to copy and paste that in just now. So here's the scenario outline. The title I gave it is the one where the shout range is respected. And it starts off by saying that Lucy is at 0, 0, because as you remember, that didn't vary between our two scenarios initially. So Lucy's at 0, 0, and Sean is at, and now it introduces this new syntax, which is some text in between a greater than and a less than sign between angle brackets. And what Cucumber does is it matches that text against the heading that it finds in the examples table that follows the scenario outline. So as you'll see, the heading of the first column, Sean's location, exactly matches the text between the angle brackets. What Cucumber does is it reads the scenario outline for each non-header row in the examples table that follows the scenario outline. It does a text substitution. It substitutes the angle brackets and the column heading with the text from that row and that column. So in this case, for the first time through, it will substitute Sean's location with 0, 900. And then it gets down to Lucy should hear, and it substitutes what Lucy hears with the text Sean. Thus, reconstituting this scenario outline combined with this first non-header row within the examples table to be exactly the same as this first scenario. Once it's executed that scenario based on the first row of the examples table and the scenario outline template, it then moves on to the second row in the examples table and again takes the scenario outline, does the text substitution, and executes the resulting scenario. So in fact, when you see the word scenario outline, what this translates into is a number of scenarios, one for each non-header row in the following examples table. So the examples table is defined by using these pipe symbols to separate subsequent columns. So this is a table with 2 columns and 3 rows. The examples keyword is used to define a table that is going to populate the preceding scenario outline. But there's another time within Cucumber, within Gherkin, where you can use a table to great effect. So let's take a look at the start of this first scenario here. Given Lucy is at 0, 0 and Sean is at 0, 900. So that's fairly straightforward, but you can imagine that as time goes on, we may have more complex contexts where we don't just have Sean and Lucy, but we maybe have several other participants that need to be located, and it's going to get quite tedious and hard to read when we keep saying given Lucy is at XY and Sean is at XZ and Oscar is at somewhere else. And so maybe we would want to represent that in a tabular format. And we can do that. Again, I'm just going to drop in a cut and pasted solution from elsewhere and talk you through what's going on. So here's the new scenario. We've rewritten that first one, but this time rather than a single step for each person, one for Lucy and one for Sean, we have a step saying given people are at, and it's supplied with a table that lists where the people are. So Lucy is at 0, 0 and Sean is at 0, 900. As you can see, the table itself is structured using pipe characters in exactly the same way as the examples table that we saw previously. However, this works somewhat differently. So let's go and see the equivalent step definition. And here it is at the top of the Shout Steps class. So first thing to point out is that even though this step definition is being supplied with a parameter which is the table that followed it. There is no capture group in this regular expression. So this is just matching the text in the step. It's not actually matching the table at all. Cucumber recognizes that there's a table that follows this step, and it packages it up and it passes it in to the step definition using a Cucumber data type called data table. So data table is a very useful general purpose data structure for capturing two-dimensional tables. And the code in here, essentially, the data table gets passed in. There's a method called cells, which transforms the internal representation into a list of strings. So essentially, every row is represented as a list of strings, and the table itself is then represented as a list of rows. So what we're doing in this code here is iterating over every row in the table. However, we're starting at row 1. Row 1 is not the first row, it's the second row. So it's a zero-based index. And the reason for this is because we want to skip the headings of the table. We're not interested in the headings for the purposes of this piece of automation. And for each non-header row, we call setLocation. We take the first column of the row, and that's the name of the person. And we then create a coordinate using the second cell of each row, which is the X coordinate, and the third cell of each row, which is the Y component. So what we're doing here is we are taking the table. The table has two non-header rows, one for Lucy, who's going to be at 0, 0, and one for Sean, who's at 0, 900. Our step definition is going to iterate over those two rows, and for each of those people, it's going to call the setLocation method on the shouty object, which is exactly what we were doing. Which is what we were doing in this scenario anyway, but before we were calling two separate step definitions. However, if you look at this implementation, it's not immediately, it's not beautiful code. It's not easy to understand. We have essentially magic numbers, so the 0, the 1, and the 2, these indices into the rows, they are not self-documenting. You have to flip backwards and forwards, and you could imagine that if there were more than 2 or 3 rows, 2 or 3 columns, it would begin to get very confusing. So it's not very tidy. It's totally correct, and it's useful to be able to work in this way. However, Cucumber for Java ships with a few really nice things that make it possible for us to make this step definition much more readable. So what Cucumber for Java will do is it will automatically convert this data table into a list of types of your choosing. So I'm going to make some changes to this code, and then we'll revisit it and see it working again. Okay, so I've made some changes, and all the changes are in the step definition class. There are no changes whatsoever that I've made in the feature file. That's exactly like we were looking at it before. However, let's look back at the step definition that we were working on. People are at. It doesn't now take a data table. It takes a list of person location objects. And now in the code, we just iterate through this list, and we still call setLocation on the shouty object, but this time we call a very expressively named method called getName on person location, and we get an expressively named getLocation method on person location. So now the actual implementation of the step definition is much easier to understand, and it will be much easier for people to pick up when they read it, and it'll be much easier for us to maintain it. We're also not having to create our own coordinate object here, so we've actually made some other improvements. It's actually tidier than the set locations in subsequent step definitions that used to do it one by one. But what we've introduced is this person location type. Where did that come from? And how does it all work? How does it hang together? So I create the person location type in the same step definition file. It could be part of your application. In this particular case, we're just creating it as a holder of parameters that are being passed between the documentation, the feature file, and the step definitions. And so it's just been very quickly knocked together. I put it in the same Java file as the step definition class, but there's no reason that you have to do that. You can put it in another part of your test hierarchy. But what you might notice is that the instance variables within person location have very familiar names. So there are 3 of them. They're called name, X, and Y, and that is exactly the same as the column headings in the data table. So the way this works is that Cucumber reads this step. It sees that it's a step that's passing a table to the step definition, and so it tries to call that step definition. It's already done the regular expression matching, and it knows that this is the method that needs to be called. It looks at the type of the parameter and sees that it is a list of person location objects that is required. It's doing this by reflection. And it then uses an underlying library to convert each row of that data table into an instance of person location. It basically does that by reflection as well. So it looks at the column headings, and it looks for properties, instance member variables with the same name in the target type, and it creates an instance and injects those values using reflection, and then puts all of those objects into a list. So there will be one person location object in the list for each non-header row in the data table, and then it passes that into the step definition. In the actual implementation of the step definition, we can do these really nice things. We can have a method called getName, which just returns the name, but we can also create our own method getLocation, which uses the coordinate constructor and passes in the X and the Y that have been taken from the data table. So the coordinate construction itself is now being localized within the person location object. So it makes for much neater, much more readable code.